this is our first Zoom colloquium of the semester. It reminds us of old times. But today it's a great pleasure to welcome Professor Benjamin Safdi for this colloquium. Ben received his undergraduate degree from the University of Colorado at Boulder. And then he went to Cambridge University, where he got a Master of Advanced Study as a Churchill Scholar. It's a prestigious scholarship to have. And then he did his PhD from Princeton University in 2014. He was then a Pappalardo Fellow at MIT. And then he went to University of Michigan, Ann Arbor, on the faculty. And finally, he moved in 2020 to LBNL and then to University of Berkeley, UC Berkeley, in 2021. I know Ben because of his work on axions and sort of beautiful simulations and sort of very large simulations, cosmological simulation of axion dark matter. And he's going to tell us more about that program in this colloquium called The Search for Axion Dark Matter. Ben, take it away.
Thanks a lot. Can you hear me okay?
Yes.
Can you see my screen? Okay. Please feel free to interrupt in whatever way you can if you have any questions during the talk. No need to wait till the end. So first, I'm very sad to not be there with you all in person, but I hope I have the chance to visit at some later time and connect with you all. I'm not too far away, being in California. So today, I want to tell you about the search for axion dark matter. But before we talk about dark matter, let's just talk a little bit about stars. So when you stare up at the night sky and see a beautiful scene like this, a pretty crazy thing to keep in mind is that essentially everything that you can see with your eye when you look up at the sky, we understand what it is. Mostly you're seeing stars, and we know what stars are. But it wasn't always the case. And I want to differentiate between understanding where something is on the sky, which is in some sense trivial, and understanding what something is. So for tens of thousands of years, humans have been documenting where stars are on the sky. This is a cave painting from France, and it's now thought that this cave painting from tens of thousands of years ago was actually depicting constellations that were visible on the sky at the time. But that doesn't mean that the people living in this cave understood what they were looking at. It wasn't until very recently that we understood what stars are. That is, they're powered by nuclear fusion within their cores. So to make an analogy with dark matter, we are still very much in this prehistory phase. So we've known about the existence of dark matter. I'm not going to get into the astrophysics of how we've gained confidence in the existence of dark matter, but we've known about its existence for almost 100 years. And the outstanding question today, and the question that's going to be the subject of this talk, is what is dark matter at a microscopic level? So this is a picture of a galaxy. This is not a real picture. This is a picture from a simulation. And what you're seeing is not the visible matter in the galaxy. You're seeing the dark matter that we know surrounds galaxies like our own Milky Way. If I were to put the visible part of the galaxy in this image, it would just be this tiny thing in the very center. But most of galaxies like our own Milky Way, both by volume and by mass, we know are composed of dark matter, which we expect to have all of this beautiful structure, which we can infer through the gravitational interactions of dark matter, and which we can understand through simulations. And the question that's kind of drives my research is what is this stuff and how did it come to be there in our universe? So what is the microscopic nature of dark matter? And what I mean specifically when I ask questions like this is, what is dark matter at a particle level? How does it interact with the known particles of nature, like the electron and the photon, that we're used to? And when we start asking questions like this, questions about the microscopic nature of dark matter, it's pretty fascinating how little that we know. For example, if we focus on one aspect of this particle dark matter candidate, which is its mass can span about 50 orders of magnitude from masses which are so small that, that the quantum wavelength of the dark matter is on the scale of galaxies to masses so high that the particle would collapse into a black hole. And actually, if we allow ourselves to think about black hole dark matter, primordial black holes, we can go to the right about another 100 orders of magnitude. So there's about 150 orders of magnitude of possible parameter space just in this one dimension, which is the mass. So in that sense, we know extremely little about dark matter from a particle perspective. On the other hand, that doesn't mean we don't have ideas. So you can see across this parameter space, I'm giving the names of some of the more popular dark matter candidates. And just to say kind of a philosophical aside, I personally think that we live in a very interesting time in history and scientific history where we know that dark matter exists, but we don't know what it is. And I think when you look back on this epoch of history, this is going to be a very short-lived period where we've known that most of the matter in our universe is dark, but we haven't yet identified it. And so there's a huge opportunity to be part of understanding what this stuff is. And that is the motivation that drives me to think about these problems. So today I'm going to be focusing on one particular candidate for dark matter, which is a candidate I spend a lot of time thinking about, called the axions. Axions are on the lower end of this parameter space in terms of their mass. I'm going to explain to you what this particle is, why it's motivated, how it can be dark matter, and how we might be able to discover it if it exists. So this is roughly the outline for the remainder of this talk, but it's also kind of the historical outline for axions. So axions were first introduced as the hypothetical particle of nature in the late 1970s as a solution to this problem called the strong CP problem, related to the neutron electric dipole moment. I'm going to start by explaining this problem to you and how axions could solve this problem. It was then understood about half a decade later that axions, if they exist, could also explain the dark matter in the universe. Then there's a big gap, and it's really today, I think, that the experimental efforts to look for axions are getting into full swing. And so I'll tell you about some of those exciting prospects also. So I'm going to start by explaining the theoretical motivation for the axion in terms of this strong CP problem, which I'm going to refer to by something a little bit more mundane, which is the neutron electric dipole moment puzzle. This is a puzzle related to the neutron electric dipole moment, but let me start by explaining to you the absence of such a puzzle for water. So this is water. Water is charge neutral, but there's a charge asymmetry, more positive charges on one side, negative charges on the other. And that induces an electric dipole moment, which points in the direction of that charge asymmetry. And what that means, if you put water in an electric field, it's not going to accelerate because it's charge neutral. Well, it won't linearly accelerate, but it will rotate. It'll precess. So we can estimate the magnitude of this electric dipole moment by multiplying the charge, which is separated, one electric charge, by the distance of separation, which is about 0.1 nanometers. And we estimate an EDM of about 10 to the minus 8 e-centimeters. We compare to data, and we're off by a factor of 2. So that's pretty good. So now let's zoom in on our nucleus. In our nucleus, we have protons and neutrons. I don't want to do this with the proton because the proton is charged. So if I put it in an electric field, it's just going to zip off. So let me do this with the neutron. Morally, the neutron looks the same as water. It's charge neutral, but it's composed of charge constituents, which are quarks. So you might expect there to be an electric dipole moment, which is pointing in the direction of the charge asymmetry. And what this would mean would be if I put the neutron in an electric field, it would precess, just like water does. More concretely, there's a fundamental parameter of nature, which we call theta. And a fundamental parameter is something like the electron mass or Newton's gravitational constant. It is a property of our universe which cannot change. And theta controls the magnitude of the electric dipole moment. In some sense, you can think of it as an angle in this triangle. It controls the relative orientation of these quarks within the nucleons. If theta is non-zero, which is generic, then the neutron has an electric dipole moment and it precesses in the presence of a magnetic field. If theta happened to be exactly zero, then the neutron would not precess in the presence of an electric field. So we can try to estimate the magnitude of the neutron EDM following this analogy with water. So the neutron has a size of about a femtometer, and there's again one electric charge separated between the quarks. So we can estimate an EDM of about 10⁻13 e-centimeters. If you compare to the calculation, you have this dependence on this fundamental parameter of nature, theta, which I described, and you're down by a few orders of magnitude because there's some 2's and pi's in the denominator and just some order 1 numbers, which make the number, the calculation a little bit smaller than you would have naively guessed. But the big confusion comes when you compare to data. We have yet to measure an electric dipole moment for the neutron, and the upper limit is about 10 orders of magnitude smaller than this naive theory calculation. Or more specifically, what this tells you is that this theta parameter, this fundamental parameter of nature, needs to be tuned to be very close to zero. And this is confusing. It's confusing because this parameter theta I mentioned already, you should think of it as an angle. It would naturally take values from -pi to pi. And what we've learned from data is that theta is at least 1 part in 10 billion away from zero. Why is this confusing? Because if I were to randomly create a universe, I'm going to randomly draw a value of theta, and that value is not consistent with the one that we observe in our universe. So let me repeat this. I'm going to need to do this exercise about 10 billion times before I can finally find a value of theta which is consistent with that we observe in nature. And this is an example of what in particle physics we call a fine-tuning problem. And fine-tuning problems are things that we get very excited about because they're often an indication that nature is not doing something completely lucky or unlucky, but rather that there's some underlying dynamical mechanism at play which facilitates this apparent tuning. So such a mechanism was noticed by the following people in the late 1970s. And what they noticed is that when you randomly draw a value of this theta parameter, the neutron would be in a lower energy field configuration if theta could be pushed down to zero. That is, the neutron really wants to minimize its energy by pushing theta down to zero, but it can't. Theta is a fundamental parameter of nature. That's like pushing the electron mass down to zero. It doesn't make sense. So what they did was they promoted theta to a dynamical field. That dynamical field is called the axion field. Now, when the axion, which is dynamical, minimizes its potential, at its minimum, there is no neutron electric dipole moment. So we've dynamically solved this strong CP problem. So the picture which emerges from the late 1970s is that perhaps the neutron isn't just composed of quarks and gluons, but perhaps also there are these dynamical axion particles inside of it whose job it is to minimize the energy of the neutron by canceling out the neutron electric dipole moment. So I'm going to start transitioning towards talking about axions in the context of cosmology. But to do so, let me start by just reminding you of some important epochs in the cosmological history of our universe. So this might seem completely unrelated to everything I just described to you, but this will come back and be connected. So I just want to have a brief aside to talk about the cosmological expansion of our universe. So it started with a Big Bang, a period of inflation, which is exponential expansion of space. Everything shown here in orange is speculative. We haven't confirmed this concretely, but we have strong evidence to suspect that this is what happened. Reheating is when inflation ended, and afterwards, as we go to later times, the universe behaves like a hot thermal plasma. until we hit to the QCD phase transition at temperatures on the order of a GeV. At this time, quarks and gluons become confined to form hadrons like neutrons and protons. And then the universe continues to expand and cool until we get to temperatures on the order of an MeV. I'm now coloring this in blue because this is where we start to have data, concrete data. And at temperatures on the order of an MeV, these neutrons and protons collide and form bound states, which are the light nuclei. And then the universe continues to expand and cool until we get to temperatures on the order of an EV, where we form neutral hydrogen. At this point, the CMB decouples and free streams before hitting our detectors today. So the axion would be born if it exists in some sense, which I will quantify to you what it means to be born at very, very high temperatures, temperatures on the order of, for example, 10 billion GeV, 10 billion times the temperature associated with the QC phase transition. So I also want to describe the axion in slightly more technical language. So if the following slide is unfamiliar to you, don't worry. You won't need to know anything on this slide to understand the rest of the talk. But just to frame things for the experts, I'm going to now describe that picture that I just walked you through in the language of quantum field theory. So more precisely, the neutron EDM is generated by the following term, which could have appeared in the QCD Lagrangian, where G here is the field strength for QCD. As I said, the neutron EDM is proportional to this theta parameter. So the axion solution to this problem is to promote theta to a dynamical field, which we call the axion field. This constant Fa is the so-called axion decay constant, and you can think of it as the energy scale at which the axion is born. And I'll tell you more specifically what I mean by the axion being born in a minute. And you should think of this scale as being a very large scale. Perhaps it's on the order of 10 to the 16 GeV associated with grand unification. So in this bottom right, I'm keeping track of the cosmological history. So at some very early time, high temperature, the axion is created. When we cool down and get to temperatures of order the QCD phase transition of order GeV, then QCD induces the potential for the axion. And now when the axion minimizes its potential, at the minimum, there is no neutron EDM. So this is just a more mathematical explanation of what I just explained to you in pictures. There are a few very important aspects of the axion. So in addition to coupling to the strong nuclear force, the axion also acquires a coupling to electromagnetism, which looks like AE dot B, where E and B are the electric and magnetic fields. And this is an important equation to remember. I'm going to use this throughout this talk because it allows incoming axions to hit a magnetic field and to convert into photons polarized parallel to that magnetic field. And this vertex here is the primary way that we have to experimentally probe axions. Another very important point about axions, if we expand out this potential, we see that the axion acquires a small mass. That mass, if we assume an axion is born at a scale of about 10 to 16 GeV, would be very small, on the order of a nano eV. If you're used to thinking about neutrinos, this formula might look familiar to you. This is the same sort of formula that we see in the seesaw mechanism to explain the neutrino masses. Indeed, it's physics at the same very high energy scale, which could explain the small active neutrino masses and the small mass of the axion, if axions exist. So I'm talking a lot about energy scales. So let me again take a brief aside to explain to those of you less familiar with the energy scales that we talk about when we talk about fundamental particle physics. So the least massive particle that we know of is the photon. It's massless. That's not super interesting. The particle with the smallest non-zero mass that we know of is the neutrino. These are masses on the order of, say, 10 millieV. Going up in mass, we get the electron around an MeV and the proton around a GeV. We then have a whole soup of particles going up until the most massive known particle, which is the top quark, at a mass of around 170 GeV. At higher energy scales, everything again becomes speculative, but we have reasons to suspect that potentially the electroweak force and the strong force unify into what we call the grand unified force at energy scales on the order 10 to the 16 GeV. I'll be referring to this scale throughout this talk as the gut scale. This is speculation, but there's a lot of circumstantial evidence that points in this direction. And again, we have speculation that this grand unified force merges with gravity to form a unified picture of quantum gravity and all of the other forces at an energy scale called the Planck scale around 10 to the 19 GeV. So the axion, if it exists, would be created at a very high scale, at a scale Fa, which could be associated, for example, with the scale of grand unification. So it might seem strange that physics associated with very high energies, with say 10 to the 16 GeV, could give rise to such a light particle. And the reason that high energy physics can give rise to very light particles is symmetries. The axion could emerge light because of symmetries associated with this high energy physics. And the easiest way to understand this is through the concept of spontaneous symmetry breaking. So the axions could arise as Goldstone bosons of spontaneously broken symmetries have very high energies. So imagine that we have a complex scalar field, which I'll denote here by phi, which undergoes spontaneous symmetry breaking, meaning its potential looks like the following. And so there is no unique minimum of this potential. Instead, the minimum of this potential is a circle going around at the bottom. So if we have a particle at the minimum of this potential, you can fluctuate in the so-called radial mode up and down. And in this direction, that mode has a mass because it requires some energy to fluctuate it up and down. But there's no energy required to make the particle go around the minimum of go around the circle at the minimum. And that is the Goldstone mode. It's the massless mode associated with this field, and that's what we identify as the axion. So that mass of the axion is small, or essentially zero, because it's protected by symmetries of the potential, which is generated at high energy scales. Okay, so that's all essentially I want to say about axions as a particle. And I now want to say some words about axions as dark matter. So the language that we use when we talk about axions as dark matter is very different from the language we use when we talk, for example, about WIMPs as dark matter, simply because axions have a really, really, really small mass. And what does that mean? Well, what we measure in astrophysics is the amount of mass within some fixed volume. So as I make the masses of the individual particles smaller, I need more particles to make up that same amount of mass. Axions are bosons. So as I make them smaller and smaller, I have more and more of them. They necessarily become closer and closer together. And eventually, their quantum wave functions will overlap, and I'll transition from the quantum regime to the classical regime. So by the time I get down to masses this small, we should be thinking about axion dark matter as a classical field instead of an ensemble of quantum particles. So now I have this new classical field, the axion field, and I need to include it in the equations of motion in the early universe after the Big Bang. In the homogeneous parts of those equations of motion, classical equations of motion look like the following. A here is the axion field. The dots are time derivatives. And H here is the Hubble parameter, which describes the expansion of space-time. And in the early universe, it scales like temperature squared over m Planck. So I can solve this equation in real time at very high temperatures, because at high temperatures, Hubble will dominate over the mass term. So you can forget about this mass term. And then everything has a time derivative. So in that limit, one solution is simply A equals a constant. So if I plot the solution to this equation, at very early times, the axion field is frozen at its so-called initial misalignment angle, which I'm parameterizing by this angle theta I. That remains true until Hubble becomes comparable to the mass. And after that point, this looks like a damped harmonic oscillator. And so the field will oscillate, and the coherent fluctuations of the axion field at late times will then behave like dark matter for astrophysical purposes. That doesn't mean that you get the correct abundance of dark matter. To see if you do, you have to carry out the rest of the calculation. And you'll see you get the correct abundance of dark matter for an order 1 kind of generic initial value of the axion field if you have a decay constant on the order of 10 to the 12 GeV. However, it turns out that that picture that I just described is only true in one very specific cosmological scenario, which is where the axion was born before inflation, where the spontaneous symmetry breaking happened before inflation. So when you have spontaneous symmetry breaking, if I go from Hubble patch to Hubble patch, so causally disconnected regions of spacetime, the initial value of the axion field will change. But then what inflation does is it does what it does best. It creates homogeneous initial conditions by zooming us in. So after inflation, we have created these disconnected regions of space, which will never come in causal contact with each other again, which have homogeneous initial values of the axion field. And then the calculation that I did on the previous slide makes sense, because I can talk about one single initial value of the axion field. If I were to travel extremely far spatially, which I'm not able to do, but if I were, I would find a different region of space with a different initial value of the axion field, but I can never access that. However, you have a flip of the coin to make, a cosmological flip of the coin, and the other flip lands you on this scenario. In this scenario, you have inflation at very early times, but then after inflation, the axion is born. You have this spontaneous symmetry breaking, which I'll call PQ symmetry breaking for historical reasons. That gives rise to the axion. But now, in the subsequent evolution of the universe, because we've already gone through inflation, all of these Hubble patches will come in causal contact with each other, meaning our co-moving horizon today includes in its history some average over all of these possible initial misalignment angles. So you might say, oh, you should go back to this formula and average over all of the possible initial misalignment angles. But that's actually not correct, because I wrote down the homogeneous equations of motion. And if these different Hubble patches are coming into causal contact, I should include spatial gradients. Those will be relevant. So I need to solve a more complicated differential equation. It also turns out that I linearize the equations of motion. But if I'm going over all possible initial misalignment angles, at some point the nonlinearities will also become important. And so understanding this cosmological paradigm is actually very complicated and cannot be done analytically. It's nonlinear, it's in some sense a chaotic system, and it requires numerical simulations. And so my group over the past half decade or so has been thinking a lot about how to do these numerical simulations. And I want to tell you about some of our results now. And one reason that I find this problem interesting is that in this cosmological paradigm, there is only a single mass of the axion particle, which gives the observed abundance of dark matter, because there's no dependence on initial conditions, since we're averaging over many different Hubble patches. So there's only a single number. There's a correct answer. In some sense, it's like a homework question. There is one correct answer, but it's just really, really hard to figure out what that answer is, because it's a nonlinear and challenging problem. So what do we actually do? We simulate this entire dynamics. So we start by simulating this phase transition, which gives rise to the axion as this Goldstone mode. So we start with a complex scalar field, like what I described before, that's subject to this potential. And the radial mode, the amplitude of that complex scalar field, is what I'll call the radial mode. That's a very heavy mode. And the phase of it is the axion. That's the mode that corresponds to going around the minimum of this potential. So what happens across most of space when we go through this phase transition, the radial mode is a very massive mode. And so as the universe expands and cools down, we are no longer able to excite that mode. So that mode, quote unquote, freezes out, meaning it just damps down to nothing. But the axion, since it's light and dynamical, remains throughout, even as the universe cools down, it remains dynamical. This is true everywhere, except at the location of these topological defects known as axion strings. Axion strings are very interesting field configurations. They're field configurations where if you were to go in a circle around the axion string, the axion itself, if you think about the potential, would acquire a full 2 pi phase shift. And the fact that the axion winds around the string provides a topological protection, which prevents these strings from going away. the core of these strings is actually singular in the axion-only picture, and that singularity is resolved by the radial mode again becoming dynamical at the core of these strings. So the picture you should have is that this radial mode is 0 everywhere throughout space, except at the location of these string cores. Now, the reason that it's hard to simulate this dynamics is that these strings are incredibly thin. Their thickness is physically smaller than the size of a proton, but they're also incredibly long. Physically, their lengths are larger than cosmological distances. So you need to simulate something which is very thin and very long. And that's hard if you want to fit that entire state into the memory that you have available. But these strings end up being crucial because, as we'll see, they wind around and they evolve dynamically. And as they do so, they emit axions. And it's those axions which go on to become the dark matter of our universe. So the way that we approach this problem numerically is by using an adaptive mesh. So here you can see a string from one of our simulations. In this left panel, I'm showing you the radial mode, which I said is 0 everywhere except at the location of the string core, which you can see here. As these strings evolve, they emit axions, which go on to become the dark matter. You can see that in the second panel. And the way that we simulate these strings is using an adaptive mesh, which can maintain high resolution around these string cores, but lower resolution elsewhere. So we do this in collaboration with a group here in Berkeley, which specializes on writing code for adaptive mesh refinement. And so you can see here some toy illustration of how our code works. We have different refinement levels, and those refinement levels track the locations of these string cores. And at the end of the day, we get very pretty pictures like what you're seeing here. So what you're seeing are axion strings in a snapshot of one of our simulations and the radiation that they're emitting. So I'm now going to show you an animation of one of our simulations. In the bottom left, keep track of this expanding box. That'll be the size of the cosmological horizon, the size of the observable universe, which will expand throughout the simulation. In yellow, you're seeing the axion strings. And what happens is that this is kind of a critically driven system. As the universe expands, you approach this attractor solution where the number of strings per cosmological horizon is roughly constant as a function of time. So you can see the strings slowly disappearing, but they're maintaining the scaling solution where the number per Hubble volume is approximately constant as a function of time. But what we care about is not actually these strings. We care about the radiation in the form of axions that they produce, because it's that radiation which goes on to become the dark matter. So now let me show you a snapshot of a simulation where you can see that radiation. So this is a 2D projection, and you're seeing the strings, but also the radiation that they're emitting in terms of these shock waves of axions coming off when you form kinks, or they intersect, or they just collapse under their own tension. So now we're going to zoom in, so I can show you some of this adaptive refinement. So we're zooming in around a string core. You can see here 5 different adaptive mesh refinement levels. And now we're going to zoom in even farther so we can overlay our finest grid. So this is the string core, and you can see the string width is resolved by this very fine grid. But then as we zoom out, we have coarser and coarser grids so we can fit this entire state into memory. Even doing this fancy adaptive mesh refinement, we still have to put this on the biggest supercomputers essentially available in the world and run them for a very long time in order to capture this dynamics. So the string network persists until we get to the epoch of the QC phase transition. When we hit the QC phase transition, it turns out the domain walls form between these strings. The entire network collapses and disappears, leaving behind these relic axions, which go on to become the dark matter. So this is just one more simulation showing you domain wall formation between these strings. The domain walls quickly form, collapse the whole network away, leaving behind residual axions, which become the dark matter. So these dynamics are very complicated and nonlinear. We try our best, so do other groups. And at the end of the day, we're making a prediction for the mass of the axion, which gives the correct abundance of dark matter. So I'm going to talk about the y-axis here in a second, but for the moment, just focus on the x-axis. This is the mass of the particle. As I mentioned, there is only one right answer. And our best guess for this answer at the moment is that the axion mass should be between 40 to 300 microeV, somewhere within this range. The uncertainties here are only coming from our failure as theorists to make a more accurate prediction. In principle, we should be able to compute this more accurately, and that's a subject that we're currently working on. But this prediction is important because it informs where experiments should look, which is to talk about those experiments, I'll need to talk about the y-axis, and I'll do so in a minute. But first, let me just say more broadly, I think in terms of this parameter space, there's two really well-motivated regions of mass. There's this region where the axion can naturally explain the dark matter abundance from strings if the axion is generated after inflation. As I said, though, if the axion is generated before inflation, it's a different story. In this case, there is no unique prediction because the mass is degenerate with whatever initial value of the axion field you happen to inflate from. In that case, I personally find this low mass region to be very compelling because this corresponds to high decay constants, perhaps decay constants at the gut scale. And the reasons, for example, from string theory to expect that the axion could have a decay constant at the gut scale corresponding to a very small mass. And so I spend a lot of my time thinking about such low mass axions. For example, I proposed this experiment Abracadabra and the experiments DM radio to try to go after these low mass axion, QCD axions. But I'm not going to be talking about these experiments today. I'm instead going to be focusing on this high mass region. Okay, so now let's talk about the y-axis. And this is going to be the space that we're going to live in throughout the rest of this talk. So the y-axis is parameterizing this axion coupling to electromagnetism, which I mentioned to you earlier. As I mentioned, for the QCD axion, this coupling G gamma gamma is inversely proportional to the decay constant Fa. The mass is also inversely proportional to the decay constant Fa. So for the QCD axion, G gamma gamma is proportional to the mass. You actually live on this yellow line, or up to some model dependence, you live within this roughly shaded gold region. So the particle that we really care about lives within this band or this region here. But we can also talk about more general axion-like particles, which are motivated, for example, from string theory, which could live more broadly in this parameter space. So it's interesting to look for particles anywhere, shown here, but the ones that we care about the most are the ones on this line. So everything here which is shaded a dark color is excluded by some constraint, by some search which has been done. And the regions which are lightly shaded are projections from proposed or upcoming or currently being built experiments. So you can see most of this parameter space is completely unconstrained at present, but there are proposals across much of this parameter space to search for axions in the coming years. And that's what I want to turn to now, is to look at that experimental effort to search for axions. So we're going to be using this axion interaction with electromagnetism. And so what does this allow us to do? Imagine we have an incoming axion wave, which comes in, and it hits a magnetic field. Well, it turns out that almost always nothing happens, because numerically, G gamma gamma is very close to 0. So effectively, for most purposes, this operator does not exist. But every once in a while, if we get lucky, our axion wave can come in, hit that magnetic field, and convert into an electromagnetic wave. And that's something that we can search for in astrophysics or in the laboratory. So let's understand some properties of that electromagnetic wave. If this axion is dark matter, then the energy of the quanta on this wave will be set by the mass of the axion. Energy is conserved throughout this process, and the energy of the photon is related to its frequency. So combining these relations together, we can understand that the frequency of electromagnetic radiation is set by the mass of the axion particle for axion dark matter. So then you might ask, well, where in frequency is this axion? And it's just a numerical question. And if you answer this question, you'll see that the frequencies that we care about are in the radio and the microwave band. So then you might say, great, you told me that surrounding galaxies, there's dark matter. If that dark matter is an axion, well, we also have magnetic fields in galaxies. So maybe if we look with a radio telescope, we can start to see all of this beautiful structure emerging through radio lines at a frequency set by the axion mass. And that's actually one approach to looking for axion dark matter. This is something I've worked a lot on in the past, and it's a promising way of searching for axions, in particular focusing on neutron stars, which have very strong magnetic fields. And this is one way in the future that we might be able to probe this most interesting region of axion mass parameter space, but that's not going to be the approach that I'm going to focus on today. Instead, I want to briefly explain the most promising experiments that we have for looking for axions in this region of parameter space, which are the microwave cavity experiments. And then I'll tell you about some more recent work on astrophysical probes. So these experiments, like ADMX and Haystack, are the only experiments that have yet reached sensitivity to the QCD axion. So how do they work? Well, we have a strong magnetic field in the laboratory. We have our axion, classical axion dark matter wave come through the laboratory and convert into an electromagnetic mode. That mode, it turns out, is extremely monochromatic. And the reason is that the energy of the axion is set by its mass up to small kinetic corrections coming from the fact that the axions are non-relativistic in our galaxy, but with some velocities on the order of a few hundred kilometers per second within the Milky Way. And that means that the photons that we produce should have an energy dispersion on the level of 1 part in a million. So if we have a cavity which is matched to this frequency with a very high quality factor, for example, 10 to the 6th, we can resonantly enhance this signal. So if we're talking, for example, about 25 micro EV cavities, that corresponds to a 5 centimeter cavity, 25 micro EV axions. And that's a very human scale that we can build in the laboratory. And so building these sorts of experiments has been the primary way of looking for axions for decades now. And this general idea is what has led to these constraints from ADMX and from the Haystack experiments and essentially everything else that you're seeing here. So as a theorist, I think I'm allowed to say this, the experimentalists will get mad. This region in blue here should be covered by these experiments in the coming years. I'm saying the experimentalists would get mad because that requires a lot of work and investments. It requires money. It requires the community to be behind this effort. But this is something that we can do. This technology works, and we can use it to cover this region of parameter space. But there's a Goldilocks paradox going on here, because if we want to go to lower masses, then the cavity we need would just be too large, and it's no longer feasible to do this sort of experiment. If we want to go to higher masses, the cavity would be too small, and you wouldn't have enough power to actually see the signal. So this method only works in this narrow region of parameter space. So there are other experimental ideas to go to different parts of this parameter space. I've worked a lot on this lower mass region, for example. But what I want to talk about now are some new ideas that we've come up in my group just over the past year for using astrophysics to probe this higher mass region, including this region where we predict the axion could be if it's produced after inflation. And this is coming from this paper that appeared last year on using supernova and gamma rays to look for axions. So here is very briefly the idea. We want to look for axions from a type 2 core collapse supernova. So what does this mean? Well, if you take a massive star, you're powering the star, as I already mentioned, by fusion, but that fusion process ends in iron. So you build up an iron core inside of these massive stars. Eventually, that iron core will collapse under its own gravity. It collapses inward until you get to nuclear densities. Then suddenly you can't collapse anymore. And so there's a shock wave that expands outwards, blowing up the star. But when you get to those nuclear densities, you form a protoneutron star, which then could become a neutron star. And that protoneutron star is extremely hot and can produce, for example, neutrinos. And so the only supernova we've observed so far was this in neutrinos with this nearby supernova, supernova 1987A. And the neutrino burst from the supernova lit up detectors all around the world. That neutrino burst lasted around 10 seconds. And it was coming from neutrinos, especially at late times, being produced from this cooling protoneutron star. So it turns out that these protoneutron stars, hot protoneutron stars, in addition to producing neutrinos, could also produce axions. This is something which has been known for a while. Those axions could be produced from a number of processes. For example, hot photons within the protoneutron stars hitting ions in the neutron stars, converting into axions, or two nucleons colliding together, brimming off an axion, or even more exotic processes involving pions. The typical temperatures in these systems are on the order of tens of MeV, so you expect very energetic relativistic axions with energies on the order of 100 MeV, and the time frame for these systems is on the order of 10 seconds. So what we pointed out last year is the following. Inside of these protoneutron stars, you can produce axions. Those axions are relativistic. They quickly overtake the expanding shock wave. They free stream out of the star, and then they can hit the magnetic fields which surround the star. So all stars are surrounded by magnetic fields, just like our own sun is surrounded by a magnetic field. And when those axions hit these magnetic fields, they can convert into gamma rays, because 100 MeV would be in the gamma ray band. And we can look for these gamma rays. So it turns out that there is some archival data that we can use to do this already from supernova 1987A, because there was this gamma ray telescope called the Solar Maximum Mission, which was studying the sun, but it happened to catch supernova 1987A in 1987 when this supernova went off. And it is had a blue supergiant progenitor. We understand its size quite well, and we also know, luckily, the magnetic field of this progenitor star. So we can calculate this conversion probability for axions going into photons, and we find values on the order of 10 to the minus 5 for the specific value of the axion-photon coupling. It turns out, though, that this conversion of axions into photons only works if the axion mass is below some critical value. And the reason for this is actually very intuitive. So as the axion begins to convert into a photon, you can think of you have two waves which have the same energy. And if both particles are massless, the axion and the photon, they also have the same wavelength. And that will mean that they'll always be in phase. But now imagine we slowly increase the mass of the axion. If we increase the mass of the axion, then we're modifying the dispersion relation of the axion relative to the photon. So since these two waves have the same energy, they're going to have different wavelengths. And if we propagate over some distance, you'll notice the two waves starting to become out of phase. So that phase difference is given by the momentum mismatch between the axion and the photon times the length scale over which we're propagating. And this increases as we increase the mass of the axion. So putting in the numbers for a blue supergiant, we see that we only get efficient conversion of the axion into photon if we have axion masses below a few times 10 to the minus 5 eV. So when we use the data to set a constraint on this, on the axion, you can see that the constraint is pretty much independent of the mass for masses below a few times 10 to the minus 5 eV. And then the constraint gets worse as we go to higher masses. So when we talk about axions which really behave like the QCD axion, you should actually be looking at this hashed region here. And the really exciting thing that we notice is that the region of parameter space we're able to exclude, which is this hashed region, is almost touching the QCD axion line. And this is from archival data from the late 1980s. So we are almost able to detect or exclude axions from this event which happened decades ago. And that got us thinking, well, the galactic supernova rate is around 1 per 100 years. What would we learn about axions from the next galactic supernova? What would happen if a supernova went off tomorrow? And the answer is, unfortunately, almost certainly nothing. And that is because the gamma ray telescope that we have in the sky now is the Fermi Large Area Telescope. But Fermi only sees about 1 part in 10 of the sky at any given time. So if a supernova went off, the supernova lasts for about 10 seconds. Fermi would almost certainly not be looking at the correct part of the sky and would completely miss this event. But what would happen if it did catch this event? What would happen if Fermi did see the next galactic supernova? Well, in this case, the correct line to be looking at is this dashed line down here. We project we would be able to discover anything above this dashed line, dotted line, which is any mass above about 10 to the minus 5, a few times 10 to the minus 5 eV. This covers most of that parameter space I was mentioning before, for where axions have a good chance of explaining the dark matter if they're generated after inflation. So in 10 seconds, we would discover or rule out axions over much of the possible parameter space. So it's a huge opportunity for axion physics. But the unfortunate thing is we're not even close to being ready to take advantage of this science because we don't have the correct instrumentation in space to be looking for the next galactic supernova and gamma rays. So we've made a proposal for a full sky constellation of CubeSats to monitor the gamma ray sky in this 100 to 500 MeV gamma ray range in order to monitor continuously the full sky for the next galactic supernova and for other events beyond axions. There are science applications of this beyond axions, but the application I'm focusing on right now is the axion application. We call this Galaxis. Very excitingly, we've actually started to build a prototype of this detector here at Berkeley at the Space Science Lab. So I'm hopeful that some version of this gamma ray telescope constellation will be launched over the next few years, which will enable us to be ready in the case of the next galactic supernova and potentially discover a QCD axion. So in summary, I gave you some theoretical motivations for why we care about this very specific mass range coming from axion cosmology. I talked a bit about axion experiments and showed that, that gamma ray telescope observations could have, of the next galactic supernova, could have a lot of discovery potential going into the next few years and decades. So I think if it's out there, we will find the axion. Happy to take any questions.
Okay, so we can have some questions. Just raise your hand on the chat. Maybe I'll start. Well, thank you for a wonderful talk. And
Thank you.
Yeah, even while you were talking, I was getting some text saying that what a wonderful talk. So do telescopes like SKA or CTA, or will they have any impact on?
Yeah. So the higher energy gamma ray telescopes, yeah, good. So Fermi, I should say, its energy range extends from about, well, Fermi Lat. There's also the gamma ray burst monitor, but the large area telescope extends from about 100 MeV up to about 2 TeV. And the lower energy range there, the part going from about 100 MeV up to 500 MeV, is very well suited to look for axions from supernova, because those are the energies associated with the cores of these protoneutron stars. Then when you go up to even higher energies above Fermi, TeV energies and higher, you can then detect gamma rays from the ground, because the gamma rays are so energetic that they create events in the atmosphere which shower all the way down to Earth. But at those high energies, and this is where telescopes like HESS or CTA, the upcoming Cherenkov telescope array, or MAGIC, or these other ground-based gamma ray telescopes, that's where they come into play. Those energies are too high to be accessed during supernova. So for the specific search that I'm talking about, ground-based gamma ray telescopes are not actually useful. But that doesn't mean that people don't have other ideas for how to use them to search for axions. So, for example, one idea people have played with is you could have a blazar in some very far away from us, some jet active galactic nuclei, which then creates a photon, which is converted into an axion, and the magnetic fields of that system propagates to us and then converts back into a photon, and then could be a way of making distant gamma ray sources appear brighter than they otherwise would, because the normal gamma rays would be attenuated on the CMB. And so that idea of making distant sources appear brighter is something that experiments like CTA and Hess talk about, but it's a very different idea from the one I described.
I would also be interested in axion conversion in cosmological magnetic fields. And what would that do? But that's another topic.
Yeah. So, and that's also something that people have discussed. As you know, the magnetic fields are more uncertain, but if they exist, then yes, axion photon conversion on those magnetic fields can be very promising. One thing that I'll just emphasize, though, is this, the one kind of quirky thing about this whole business, just to keep in mind, is this formula here. So if you have very extended magnetic fields, that means very long length scales, then you can only probe very low mass axions, because you want this phase shift to be less than 1. Here I'm setting it bigger than 1 because I'm asking, when does this process not happen? But if you want this process to happen, then this phase shift, ma squared over 2 omega times L, needs to be less than 1. So if you're increasing L, going to cosmological distances, that means you can only probe very small mass axions. And so that means you're probably not going to be able to probe the QCD axion using cosmic magnetic fields, although you might be able to probe axion-like particles. So the reason this particular system is promising is that it's very compact. Stars are compact. They're much more compact than, cosmology. So the length scales that enter here are relatively small, and that's what enables us to achieve such high masses.
Okay. Any other questions? I don't want to be asking all the questions.
We do have one question in the question and answer chat.
Would you let them in?
Here, do you want me to just say the question out loud? So
Sure.
from Joe, the question is, can you briefly discuss the axion solution to the strong CP problem? Does the axion field / axion density have a lower limit that keeps the strong CP behaved?
Okay. Yeah, thanks for the question. Let me try to go back and answer this question. So the kind of way I started this talk was talking about axions in the context of strong CP. So again, there's this idea that the axion is, we introduce the axion by making this theta parameter dynamical. And the strong CP problem is this problem that if I generically just choose value of this theta parameter, which is a fundamental parameter of nature, I would have a neutron electric dipole moment. And we don't observe one. So he promoted to this axion field. When this field minimizes potential, it removes that electric dipole moment. But perhaps what this question is getting at is that if the axion is dark matter, then actually it's not, we don't just minimize its potential. We have now a dark matter bath of axions, and those axions are oscillating. And what that does is it wiggles the neutron electric dipole moment. So if axions are dark matter, then the neutron electric dipole moment is not actually 0. It is a non-zero value which is oscillating in time at a frequency given by the mass of the axion. And this comes from the residual abundance of axions that we have left over as dark matter. And so actually you would expect this white ball here to be oscillating back and forth at a frequency set by the mass of the axion. That frequency could be kilohertz or megahertz or gigahertz. It's a very human frequency that we're talking about. And there are experiments that look for this. Maybe some of the more promising ones are Casper and Casper-Wind. And these are experiments which look for neutron precession, neutron spin precession in the presence of axion dark matter. It's a very promising way of trying to search for axion dark matter, but it's not something that I touched on today.
Any other questions?
We also have Matthew Baumgart has his hand raised, so I'm going to allow him to talk.
Sure.
Hi, Ben. Very, very nice talk.
Thank you.
I wanted to ask, the possible bounds from axion superradiance, is that something that's on, I when I see all the different types of limits, I start to lose track of them. But is that somewhere on your plot? Is that something that's more relevant for axion like particles compared to the QCD axion? Anyway, I just wondered if you could comment on that.
Yeah. Let me get back to this. Yeah, good question. Good to see you. Let me get
Likewise.
back to this plot. Okay. So black hole superradiance is not on this plot. It's a very good question. It's not on this plot for essentially because it would not show up. So yeah. So first, let me explain what black hole superradiance is, just for everybody else. So this is the idea. I'm not going to explain the whole thing because it's very complicated. But if you have a spinning black hole, and if you have an axion, it doesn't have to be dark matter, but if you have an axion whose quantum wavelength is comparable to the size of the horizon of that black hole, then there is a resonant instability where that black hole can spin down by producing a cloud of axions surrounding it. So you have a very rapidly spinning black hole and it spins down. If axions exist with a wavelength comparable to the Schwarzschild radius. So what people have done is they've then measured black hole spins at different masses. So the mass determines the Schwarzschild radius, and then you measure the spin. And by noticing that there exists solar mass black holes with spins pretty close to maximal, you can set a constraint on the existence of axions at those masses. So if you just, then it's a numerical question of you have to convert a Schwarzschild radius into a mass, right? You're asking if I convert this mass into a Compton wavelength, what Schwarzschild radius does it correspond to for a solar mass black hole? So you put in those numbers and you get numbers right around 10⁻12 eV. So in this parameter space, within a factor of a few of 10⁻12 eV, there are constraints coming from black hole superradiance. They're actually not shown here because they would, as you increase the axion-photon coupling, you can destabilize that superradiant cloud and you can ruin that process. So if I were to go down on this plot to couplings not shown, but the ones that do intersect the QCD axion, there are constraints there from black hole superradiance, and they are relevant. They're not relevant in the region of parameter space that I'm talking about, but they're relevant for even lighter QCD axions. So they're definitely like part of the ecosystem of strategies that we're using to try to search for the QCD axion. They are a relevant process. You'll also hear people talk about black hole superradiance for supermassive black holes. You can play the same game for like the black hole at the center of the Milky Way or some other galaxy. Those Schwarzschild radii are larger, so the masses you're probing are smaller, and those appear way to the left and aren't actually relevant for the QCD axion, but are relevant for axion-like particles. So the quick summary to your question is, yes, there is a narrow region of parameter space where black hole superradiance is relevant for the QCD axion, and it's also extremely relevant for axion-like particles, but this is all at lower masses than what I talked about today.
Okay, thanks, Ben.
Yeah.
Any other questions? No. Okay, well, thank you very much for a wonderful colloquium.
Thank you.
We all learned a lot. Thank you.
Thanks a lot.
Thank you.
All right. Bye.
Thank you.